going to do today, solid modeling. We've done it before. This is probably the third seminar I've done on solid modeling and meshing, and the message is a little bit different, a little bit of the same, a little bit different, but there's always something new coming up on how to do it. So, and all this material, what you're seeing here, we're recording it. It's going to be put on the web, they'll get there in a couple of days. And the models that I'm using, most of them are just generic. So the models that are generic are going to be also uploaded along with the video and these notes that you're seeing here. And on the outline, what are we going to cover? We're going to talk about how we mesh complicated geometry. This is not a demo. It's how we do it for simulation projects, and also some of our tips and tricks, how we approach hexing meshes. And I feel there's so much marketing about hexing. They want to show impossible piece of geometry and say, look at this, we've hexed it. And then you find out, if you actually dug into it, that it created hexahedral elements that are so warped and distorted that they're unusable so much. You would be almost dinged. You'd be dinged for using them because they're so distorted. So we're going to show engineering practices and not marketing. This is a seminar for simulation engineers, and I like to say it's independent of the interface. That what we're showing is I think pretty much out there with all the FEA preprocessors. So this is for how would you say it? Professional development hours. If you're a professional engineer, you might have heard that. And I'm sure this is classified for an hour of professional development. And I also want to say thank you for attending, because if you're here, you're interested in keeping your skill set sharp and improving it, so you should give yourself a pat on the back. And good job keeping the skill sets. Okay, a chunk of junk, or I might say a potato. And people talk about solid meshing, and there's so many different skill sets involved. FEA can be easy, FEA can be really hard. Just depends on what you have to do in your daily work. So let's talk about it. Let's go in. And we run into all sorts of things. Jeremy and I, we see a lot of stuff out there. It's quite entertaining. And I still remember someone telling me that, like, wow, the FEMAP, it's hard to use. And I don't care. I mean, I'm a generalist. I think all the tools now, they can't get any easier. So I got to start off with a demo and say, okay, look, let's see if I can't mesh this, in 10 steps. So let's find the models. Let's just get the demo over with and bring it in parasolid geometry scale factor. There we go. And then we can go into using the tree, right click, tet mesh, and I'll make it out of aluminum, 1e to the 7.3. Isotropic, all you need is two properties. There, it's meshed. And the lower left-hand corner, I keep track of, the nodes and the elements of what's going on. It's pretty small. Now that we have it meshed, let's put on our boundary conditions. And I'm going to use this thing here. It's a selector. I'm going to work on surfaces. And it highlights the surface that I want. I click, right-click, and we'll constrain it. And I don't need a name since there's only one. And then I'll go over here and I'll put a load on it right there. Come down, load. Like that. So I brought in geometry. I meshed it with some tets. I loaded it up. Now I can analyze it. New, Sim Center, static. Hit OK, analyze. That's it. There we are. We're a solid modeling genius. So it runs. It got done. Here's the statistics on it. And we can go to deform. It comes up. It recognizes we want to do deformed. Contour, like that. I can double click to redraw. And there we have our stresses. Now you're seeing the on the screen, you're seeing the geometry from before. And there's a little shortcut. I'm going to hit Control Q, which brings up these visibility options, and I'll just turn all off. My model, it disappears. And hit like that. There we go. There, 158,000. Now, this material, before, yeah, there you go. I didn't count, but I don't think you can get any easier than this. And when you were looking at stresses, since we are talking solid modeling, and you can see it's still highlighting surfaces, so I'll turn that off there. I do want to talk a little bit about convergence, because everyone, all FEA people, we love to converge meshes. We love to mesh. It's simple. Drink some coffee, hang out, look at the pretty mesh. We look at that and go, yeah, but what's really going on? This selector here, if you turn it to element and pick on that element, if you look on the lower left-hand corner, these are panes, and I got the entity info pane turned on. And I hope you guys see it. It gives the stress at the centroid and the stress at the corner points. And if I'm really picking around for stresses, I like looking and comparing the centroid, which are stresses interpolated from the integration points to the center, as versus stresses that are extrapolated out to the corner points using the isoperimetric function, the shape function for the element. And I like to say, okay, the amount of work being done by the shape function is the difference between the centroid out to the nodal points. And of course, the nodal points, the stresses are averaged with other elements, because elements computationally are solved as islands with their nodal stresses, and then they're dumped out, and the stresses at nodal points are averaged. So we see we have at the centroid, we have 130, and at the corner points, we have 160. So we have a delta of 30. So what we got, like a 20% work function going from 130 to 160. 20%, not bad. It's not 50%. Seems reasonable. One of the things we can do here, which you got to do this because it's cool, is say, wow, let's remesh, let's refine the mesh and get a better value. So we'll go into the meshing toolbox, mesh sizing, and I'll set this to 4 like that, and dialog select, and I'll just do brute force. I'll just grab all these curves and say remesh it, and I go, I want more. Right click, previous command, and okay, back to there. There we go. That's getting more like it. There we go. We'll rerun that, because you know what's going to happen. We'll come back. It'll run. It'll look smoother. Usual stuff. But what I'm showing here is that you can use the toolbox. You can update meshes on existing structures. Come back in. There's all sorts of things you can do. And there's our, go back to post-processing, look at contours, and you go, wow, holy moly, doesn't that look fantastic? Isn't that so much better? Well, look at the stress. It's gone from 160 to 168. So it bumped up 5% on it. So much for that. What I use this for, we use this model in a class for meshing. And let me go back to the notes. I keep track of what I'm doing, because I have a little blurb on the bottom. What is verification as compared to validation? And why do so many simulation engineers think that mesh refinement makes an accurate analysis? Well, it's fun to do. We don't have to think. We just refine the mesh and pat ourselves on the back. We use this in class because this part here has a yield stress of 100,000. So anything over 100,000, it's like, well, that's not going to work. And why was it over so high is because we were given loads that someone pulled out of, well, we won't say where they pulled them from, but they said, oh, use 40 pounds because we want to be conservative. So get this. They were applying this 40-pound load on this little surgical anvil as part of their QA. And if it passed, they would sterilize it and ship it off to the doctor. And then the part would fail, not always, but occasionally inside the patient, and they couldn't figure it out. And they were shipping pre-cracked parts. So what was the solution? Well, they went back and verified that really the load should be 14 pounds and not 40 pounds. So it had to do with loads, had nothing to do, but spent a lot of time chasing our tails, remeshing and redesigning when it was a bad load. So verification is compared to validation. Verification is that you check your model, you check mass, check dimensions, check loads. That's verification. Hand cranks, verification. Validation is accuracy, is against a result, an experimental result. Now, it's not perfect. There's a very nice section that you can get from ASME on verification and validation. It costs $60. We got the book in the office. So we actually sent one of the engineers to the short course they give. It's really, really interesting. You know, they flat out come out and say, look, validation is not the holy grail. You can still screw up an experiment, and you have to put bounds on where you think your experiment is and bounds on your model. But it is the grail. So verification. And what I find amazing is that, yes, very experienced engineers will confuse verification with validation. Say, oh, my model was validated against hand calculations. And you, painful. And it happens. But now, look, you guys won't do that. You've heard my horror stories. So now that we've got through the demo, hey, Max, any questions out there?
Nothing so far. Looking good.
Not worries, on mute. Okay. How's my reception? Am I going fast, slow?
I think the pace is pretty good. Sounds clear too.
Good, cool. I'm on a headset. All right. Now let's do something real. No more demo. Let's see if I can get something to crash, because I really don't like, you know, making it practicing too much. You know, you got to have some drama. So I love this part. This is it's the truck hub, symmetric, complicated geometry. And what are we going to do? Well, it's obvious, of course. You bring it in, it fails meshing, and what do you? Well, a lot. It's a workflow, but I'm going to throw in a little trick here. We're going to talk about the mesh preparation and what it does compared to other things. And yes, we can adjust it and clean it up. And that's part of the gig. Is that I'm going to show how to, you know, what you can do in the toolbox. But the real trick to it is that once we show we can get it to mesh, is that we're going to go back in and skin it with tries and do it right to get a quality mesh. So the first part is like, well, you know, run, gun, go straight to solids. And since and the mesh sizing, because I don't want to bore you guys hanging around here too long and waiting. And off we go to the races. Dun, 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 dun. Lots of degenerate measure aborted, and it comes up and it'll give you some symbols that show where it couldn't close out the surface, you know, where it failed. And so, and we could fix it, but for a solid like this, FEMAP has this geometry preparation tool. And what it does, it looks at small skins and slices and dices and tries to fit an appropriate surface that reflects the sizing parameter that you give it. I'm giving it a sizing parameter of 0.15. And so what it wants to do, it'll adjust the geometry to fit that sizing parameter of 0.15. And pretty much everybody has these tricks. I mean, for example, in other Siemens products, they put a wrapper around your geometry. They just wrap it, and then you mesh the wrapper. That's really good for CFD because you don't want small holes and little crapola, because you really can't resolve turbulence a lot of these small features when you're looking at a model this size. But in FEA, you want small features. It's like small features lead to fatigue cracks and dangerous stuff. So the approach on the FEMAP team is that they keep all the small features, but they try to blend it on the surfaces so that your small features don't kill your mesh. And you can see it meshes, and I don't know many people do this. It's one of those things that I start recently doing after all these years. I actually look at the statistics now. Isn't it crazy? You know, it's like so many years of this stuff, and now it's like, no, this is really cool information. It's like, you know, like how skinny and nasty your elements are, because you guys have been in this game, you know that in a perfect world, we'd all have elements. They're solid elements that go one by one by one, because we would have perfect Gaussian integration, and we would have perfectly numerically calculated volume, which would give us the best stiffness calculation. And as we start deviating from one by one by one, it gets harder and harder to calculate the volume. And with a poor volume calculation, we get poor stiffness calculation. With poor stiffness, we get poor deflection and poor stress results. So these numbers are quite good to look at. And you can see we don't have anything over 100, but we got plenty. You look at this, and we got some over 9.9 on a Jacobian. And for solid elements, the Jacobian rules. It doesn't work as well for shells, because shells warping can just kill you. I've had my ass handed to me enough times on warping of shells to be scared about it. I use this a lot. I like looking at the contour data. I'll look at, you can warping, Jacobian, and if you're doing LS Dyna work, you can also do your explicit time step. And we want to look at the Jacobian. And it comes up, and you say 0.93, you groan, and you start looking at it, and you realize, you know, you go in here, and you go, yeah, you know, it tries to clean up, but you know, it's sort of, you can't do everything. I'm going to undo. Before I go into it, you guys may say, well, what's going on with these weird ass colors? That is a mesh preparation, and everything can be tweaked and undone within the toolbox. These are combined surfaces, and the blue lines are combined curves. So if you want to modify stuff, the hierarchy is you got to get rid of the combined curves first. And I'll go to method on surface like that. So you get rid of the combined surface, and then you can go in and get rid of that combined surface like that. It's when you first look at it, it's intimidating because it's so powerful. Go find me something that's powerful and easy to use. We know that swag, and it's just the nature of the beast. You have a lot of control on how to get a good surface, and the mesh prep is your first stab at it. Okay, so I'm going to undo and go back to where I was. Now you've seen the razzle dazzle. Let's go do it the real way, is where we're going to skin it with the surface mesh only, and then we'll do some cleanup on it, and we'll beat it down so we get a better surface. So on that, it's the same thing. We're going into solids, but we click this right here, surface mesh only. And when we turn on the Jacobian, it comes up with the same pieces of crap. And it's these thin surfaces, these small little surfaces here, and you're going, and I've measured it and stuff, and you guys don't need to see that. We're just going to go into feature suppression by curves, and I'm just going to say, so kill them. And the limit size, I know, it's 0.015, like that. That's what I want to go. So it's going to shorter than 0.15, and then dialog select is just the whole solid. Go, baby, go. So that got it down to 0.192, and come back here. Now I want to go in and change the mesh sizing, and I'm going to increase it. And the advantage of working with just the tries on the surface is that it goes a lot faster. You know, because all it's doing is having to update the sizing on the surface, and there is, where is the next one? Like that. Plus, this is quite fun. This is, you know, hacking on meshes. It is addicting, and I hope I'm not making you guys dizzy with the mouse and the movement going around and around. But, so now I'm down to 846, and now you go mesh, geometry, solids, and it takes what you got, meshes it, and we're 0.822. And then you look at the statistics and you go, yeah, there we go. We only have one element, about 0.8. That is a good mesh. Now, of course, yeah, it's one of those engineering things. If the distorted elements are in a low stress region, it doesn't matter because there's low gradient. And so it's good to go. It's all, you know, high stresses, you want good elements, of course. So, well, but takes care of this. So where am I? 855. Not bad. Okay. Defeaturing. I don't know. I felt sort of, this is just so, it's a meshing toolbox thing. And I don't know how many of you guys get into it. Let me bring it up. I just sort of show it because it's, how you say, people are reluctant at times to really jump in and use the toolbox, and they say, well, you know, I got a CAD tool, or send it back. But sometimes the CAD tool is not accessible, the guy's not around, who knows, or it gets too complicated. So I just wanted to show, because get rid of blends. And this is one of those things. DMAP continually improves on what's going on. It's like, if you use a version, like, let's say a year earlier, things would break. A lot of these operations just wouldn't work. And so, I got limit size turned on, so it's not allowing me to go. And so it's like they're always making improvements in what's going on. And so, you know, if someone says, well, I tried that, didn't work, and well, what version are you using? And that's another thing. You may notice if you're doing tech support with us, we come out of the gate and say, okay, what version are you doing? And if you're using a really old version, he says, wait, let's try the new version. So this is one of the things that I've been using. It's split solid, and I'm going to do it to make a washer. And check this out, alignment. You can do it by a tangent to a curve. And now this isn't too special because it's, you know, it's not on a curve boundary and stuff, but see, you can put washers. Of course, that's a pretty big ass washer. I made it a little too big, but it splits your solid for you, and it aligns the splits. I know I'm sort of obsessive compulsive on meshing, but it's when you start doing a lot of washers and you're trying to get a really good mesh, and you're doing aerospace work, and you know people are going to be reviewing it, and your quality and stuff, and it sounds weird, but you want your washers to be sort of aligned right. And the reason why we use washers on our connections is that when you're doing RBE2s on your washers, it really is nice to use a washer and use an RBE2 because it gives you better behavior, gives you more realistic behavior. So we've really been keen on washers on everything. So now hexing, my deep infatuation and craziness. The reason why I like hexing so much is that when you look at stresses on a hex mesh, they're really smooth and clean. And the reason why is that the integration points on a quad are nicely aligned to the surface. If you have good, clean quads, integration points are really sweet, and it gives clean extrapolation out to the nodes. When you're doing a TET mesh, the integration points are all cattywampus. I mean, yes, they're ordered within the TET, but you got to think of a TET, you're just dumping them into a bucket, and the integration points are all over the place. I find it almost, you know, yes, you use enough TETs, you get a smooth looking contour, but painful. Where hexes, you come almost out of the gate with a nice look. It should be noted that the 8-node hex is an incompatible isoparametric element. It's quasi-parabolic. It has an extra shape function so that the edge without a node can bend, which means if you have two hexes together, one can bend down and the other up. I'm going to leave it at that. You mathematically inclined engineers can go check that out, but it's not linear. The true parabolic, well, not quasi, parabolic, is the 20-node hex, and of course the 10-node TET. And I've been starting to use two of the 20-node TETs in regions of interest because you get even cleaner and even more beautiful looking results. So this is one of the tricks. Well, I want to show this model, not get too much. I'm going to show something on hexing here on the next slide, but the one on the left is a gigantic discharge nozzle that's got how many meters in diameter. It's 4 meters in diameter, top to bottom. It goes onto an hydroelectric dam, and we needed really detailed stresses in it. And so you can imagine if I did it, and it's contact. Notice on the right we have bolts. That's a bolted flange, preloaded. And so it's one of those things, running it as 5 million nodes. Of course you can. Yeah, you bet. SimCenter Nastran has really evolved in speed. Again, the last couple of years. Used to be just embarrassingly slow, so to speak, but they fixed that. But this model with 890,000 nodes with full contact will go through the full bolt load and apply the loads. And I'm using CFD loads on the inside. It'll take about 20 minutes. It seems amazing. And if I did it in TETs, it would take a couple hours or longer. So, and you can see what I'm doing is, and I've covered this before in prior seminars, the classic, you got a TET mesh, you glue it to your hex mesh. Don't be afraid. It'll look good to do it right. And I got about 10 years invested in that glued connection technology. But how do you know if your mesh is converged on stuff? And I've wrestled with this. I mean, I like centroid, nodal, but there's another cool little trick we've been doing. Look at the normal modes, because the normal modes analysis tells you the permissible deformation behavior of the structure. Permissible deformation behavior. So if the normal modes match up, and I'm showing the first 4, then you're in pretty good shape. Of course, you'd like to see, it depends where you need to go. Of course, it's nicer to see higher frequency. But in this case, the first mode is the bending mode, and that's what this structure responds to, bending. And of course, the higher modes are these weird ass torsional modes, and you can tell it gets, it degrades a little bit. But that's what we've been doing, is that when we're idealizing structures down to go into assemblies, is that we'll take a component, TET mesh the bejesus out of it, like 2 million nodes, right? And then we'll have our itty bitty little idealized shell model or hex model that has like 2,000, 3,000 nodes, and we'll compare the normal modes to it. And that's how we build structures, is you can do that. It really makes a nice documentation trail. So, but nothing's perfect. Just one way to do it. Okay, let's get a little meat and potatoes into hexing, because I've been glossing over a little bit. I'm sure if you guys have been hexing, you end up with the angry red hex structure, and you go, it's impossible. It must be, it's the software. I'm going to get rid of it. But let's talk about that. Let's go through it. And yes, I always want better hexing capabilities. I always, it's like bar none. Give me, So what I'm going to do here is like first I got to drill into it, and I'm setting up the work plane on the surface, and I'm going to make a circle at the center of gravity of surface, and 0.25 like that, and I'll go here, and I got to imprint it with that circle like that, and then I'll go into geometry, solid. And I always say, this is being recorded, so yeah, I'm flying along. Don't, which solid do I want to delete? I thought I imprinted that. Oh, I didn't. I imprinted the other. Okay, what's going on here? No, oh, I know what I did. Undo. Come back here. There we go. For you guys new, undo, it's a Windows program, and I hit Control Z. There we go. I want to get rid of that. Right click, delete. So I'm going to take a first stab at it, and it's like how this happened. Before I do that, you can see in the report I have a nice washer around it, and just to repeat that, slice distance 0.25 on the radius, tangent to curve. Fine, I'll make a tangent to that. Distance, extend, all these little picks, and I've been there with it doesn't work. It stopped working. So what I'll do here when I'm hexing is, if I'm doing a lot, I'll make a little toolbar, customized toolbar. I have all these things. And it gives you the angry red, but it likes that. And then you go in here, solid. You can see why I make a toolbar on it. And I'm going to hit repeated slicing. And global, how do I want to do it? Surface normal, like this surface here, on this point here, like that, right? And what I would do, how it goes, and then I would show like, this is only red, and this will be hexable. You guys know where it's going to go. So I'll take that, I'll slice it like that, right? And now I can go back in here, size on solid, run, gun, and it all allows you. Now, behind the scenes, the way hexing is working, it's changing colors, and it's setting up mesh approaches. And mesh approaches, if you're unfamiliar with it, it's classic, read the manual. There's no easy lunch. What it's doing is it meshes one surface as a master, and then it uses that mesh surface on the next solid. And it's just a way to link meshes up so that you don't have gaps. You don't have holes in your mesh. And on hexing, it links it sideways, upways, things, and there's a nice little section of the manual how it sets up the priority. But once you get into the swing of things and think about a solid and pushing a mesh forward through the structure and how it behaves and the linking on it, how it thinks as a hex, it's a really powerful. And you can figure out how to hex almost everything after a while. Once you understand the theory, you can see how it pushed it through with the hole, and everything is groovy on that. Now, one of the things they've added is this transition to be able to blend text to hex. And I never really got cared much because just glue it, glue it is fine. But in modeling, it's like one more thing to keep track of. And so now they have this cool little hex to tet, and I want to touch on it because it is nice, and I've been using it. So where is it? Why be clever with I call it, yeah, be clever with your mesh battles, because not everything has to be a tet, and not everything has to be a hex. So I brought this up. What I'm going to do is use my favorite embed face tool here. I'm going to pick this face and this face here to drive it through like that. And then I'll go back here, and I want to add these back together. That's another tool I would put it in there. So I have 3 solids set up for this, and I've already preloaded the hex and tet into it like that. And this is the gig, is that you go in and you start declaring it that you want to make it a hex. And it doesn't look very pretty with that mesh sizing. There we go. I'll make a prettier mesh. And it'll come back and says, oh, look at this. The blue is it can hex. The red, it's unhappy, it won't make it. But so what you do is you go on your hex, what you can hex, like that. See, okay, to skip meshing, yeah. Well, it has a little history, right? So I'm going to put no, and I'm going to hit it with the hex like that, because I have colors assigned. And you can see we have a beautiful hex surface. And the reason why you want to hex on this is contact. And this is nasty, nasty, nonlinear contact. And there's nothing like a regular repeating pattern mesh surface to give you good contact behavior. As versus, I mean, you can get there with tets, but you got to be careful. It's a bit of a battle. But hexes, it's quite glorious. So, and then you go to this other part, and this is where it comes up, and it says, oh, tet pyramid. Okay, let's do that. And you hit it, and it will echo down here. It says inserting pyramid mesh. And it will go ahead and insert that in. And okay, what is it going to do? Just where it's going to come up. Oh, there we go. Oh, I got the wrong color. Darn it. Well, that's fine enough. It should have come in with a different color. And so, but what I can do, update property ID in solid. Yeah, I got to change it back to het. There we go. Color is important. So what it's done is puts a pyramid mesh, and you can verify that by using your selector, going there. There's your pyramid. So you have a super clean transition. No gluing to remember. You don't have to track that you glued this interface with that interface, and it's just done. So there. Max, still alive there? Everybody, they're not falling asleep?
Doing well. Yeah, okay. We had one question come up, but I think you answered it, so it should be good to go.
Okay. Yeah. Oh, I didn't say like when hexing rules. Oh, that's a caterpillar track, gear tooth thing, everything, little symmetry model for, and it's those rings. It's to pull a gigantic chain. It's a gigantic piece of mining equipment, and they didn't size it correctly, and so they were breaking bolts, and the whole mine site was down, and it was a long study, but we did so many different iterations. We had to hex. I mean, hexing was fantastic on that because the model was fast, and so many iterations, and it's it's like. Everyone says, tetting works fine. It does work fine, but it can get real addicting. I want to bring this up because it got me, and I only noticed it because I was looking at stresses and I was going, what the hell? I want to show stress contours for the pyramid mesh, and what we're doing here is we have a 20 node brick on the inside, where it's picking up high stresses, merging out to an 8 node brick. So let's show that. And mixed meshes. So we got 10 node tets. One, you got the pyramids, duh. And then you got this classic, and this is what you would come out of the gate with. You'd mesh it, happy-go-lucky, 20 node, it merge up to your 8 node, and you're going to pull it, and you would say, everything's fine. So let's see if it's going to run or it's going to bark at me. Dun, 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 dun. 9 seconds. And it comes up, and I was starting to look at it, not this model, but like the real model, and I was going, that's not right. How do you go red to like nothing, and how do you go like this color to something is not right? And of course you look down here and you go, ooh, it's like, I call it, it's like, okay, what's your test of meshing? Like, how do you know if it's converged? Is it smooth? And I think, guys, you've heard this thing, if you turned off your edge outlines, does it look realistic? Or can you see mesh splotches? So you look at this and you go, yep, that's good enough. And there's no way you could see an interface. And if I was really picky, I'd show the same model without the pyramids, like with a glued interface, and see if you get the same behavior. But I've really started to use it a lot. And if you look and you do your research on the pyramid element, it is, it's another isoparametric, but it has a very clean shape function match between the TET and the 8 node. And there's scientific papers, research papers that show it's all good. So what do we do here on it? Let's go back in. You guys notice that I didn't automatically hit F5, the view options, and it's hard to break habits. I'm trying to get to using more of the toolbox. Update elements, connect. And if you read the manual, you go, oh, duh, connect. Add mid-side nodes to linear edges. Okay, cool, let's do that. And it will, nicely enough, it'll tell you what elements it mucked with. Isn't that cool? So it added mid-side nodes to those 8 node bricks right there. So now they're not 8 node bricks, they have 4 extra nodes. So now they're 12 node bricks. So, and it's legal. And then you rerun it. Dun, 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 dun. I think it takes longer to unload and load. So then when you look at the contours, you go, oh, okay. Now, it's not perfect. You would look at this and go, oh, that's bullshit. You don't go like that, or like, well, what happened here? So yes, well, and that's because, I mean, you dug into, remember, it's averaging stresses here from the elements and from the nodes isoparametric. So it's got to be funky going for these different, nodes and elements. If it was perfect, it would be even more suspicious. But then when you step back and you go, okay, you get, it's not perfect. You get this sort of behavior here, but it's generally smooth and groovy. Now, if this was real work, I would just extend out the 20 node a bit farther so that there's less of a gradient, and then you wouldn't see this pop out as much, but it makes a good, quick little example. So be careful joining, modify, mix meshes. That's it. I'm wrapping up on it.
Hey, George, we had a question come up. Okay. What was the exact command that you used to match the hex with the TET mesh?
Okay. There's no exact command. So what FEMAP is doing is that you have to have slave surface mass. You have to have slave surfaces between your TET and your hex. It's a little sneaky, and first it looks for, it has to have, you know, that slave surface transfer done. So that's why I started out, you know, I said, okay, I'm going to hex mesh, try to hex mesh the whole thing, and you can see my screen. And so that sets up the relationship, the approach on surface relationship automatically. Okay, then I hex meshed it, and then of course I saved the TET part for the last. And so when you TET mesh it, the default, let me show the default, because it's something that I wasn't quite, you know, I wondered about it, like, what the hell are they doing? The default is to hunt for that relationship, hunt for that surface that has quads on it. Well, quads, well, ain't no bricks, but I think you guys know what I mean, like a quad surface. Hunt for that, because you get the relationship, approach on surface, and as it sees that, slap some pyramids on it. So there's no exact pyramid come in. It's within here, auto mesh solid. And so you guys will hear this from me. It's like, well, build a small model, and you'll see it too. It's one of these seminars are, you know, a little bit of love-hate because it takes time to set up, but I always learn something from them. I learn a lot. It's when you have to really get down and explain it, it helps you get rid of bad habits. So, done? What do you think, Max?
Pretty good. We did have one more question come up.
Sure.
The question is, does the hex mesh face have to be associated with the solid of the surface?
It has to be associated with the approach on surface. So it has to be, yes, that hex element has to be associated with the surface that's tied to approach on surface. That's a double one. I would say if it's, you know, to the questioner, take a solid, whack it in half, and play with it, and you'll see it. You'll see it clearly, or maybe not. If he doesn't see it and you're confused, you know, if he doesn't see it and you get lost, give us a shout. Give us a shout, and we're happy to dig into it. So, okay, we like to keep these punctual, under an hour, because attention span. I gotta go. If you have more questions, send an email to Jeremy. He's there. He's alive. I want to mention this because you guys, it's the iterative solver, and it's within the analysis thing. And most people, I don't know if everyone really sees it. So what I want to do is, if you have a chunk of junk that's all TETs, then it's about 10x faster. And this is where it's number 2, iterative, elemental iterative. So, but it's for 10 node tetrahedral meshes. You can't do it with normal modes analysis, and it won't work with shells. There's all sorts of limitations, so that's why it's not a default. But it's there. If you're doing it'll run things super fast. Here's my comment. If it looks good, most likely it's good. You heard me go on about Jacobian, element contours. Hey, and again, good job for hanging in there. I'm working on you know, improving your skill set. It's really good. It's important. If you guys want to know more about isoperimetric elements, I have a nice little fluffy article on visualization on true colors, and you can find it on the applied site. If you're not, ping Jeremy, and he'll ping our digital marketing specialist to make it, you know, more visible on a searching. Remember, stress flows, area stress function continuous. You have a hole in a plate, 3x minus. And I do have more stuff on solid geometry meshing from TED to Hex as a seminar. There we go, 9:23. Jeremy, Max, thank you.
Yes, sir. Thanks everybody for joining us too.
Yeah. All right. Thanks everybody.
Thanks everybody. Shutting it down. Have a good day. Thanks for coming.
Cheers, everybody. Bye.